Alright, so in this video we'll talk about addition of vectors, but rather than the geometrical method that we actually ended up using in our previous videos, we will use a more analytical method. Let me just write down that here, analytical method, to add vectors. Alright, so let me get rid of this for the moment. Alright, so like always, we'll start with our vector coordinate system, and let me draw that here. So my x and my y axis, x here, y there. My first choice of vector, say vector A. Vector A is somewhere here. All right, this is my vector A. My second choice of vector, vector B. Let me draw vector B from here. So this is vector B. And the reason I'm drawing it from the head of vector A is because we want to see how our geometrical method plays out in our coordinate system. That means our geometrical method, which involved placing the vectors from head to tail in such a manner that the final vector from the tail to the head would yield the resultant, or A plus B, if this were A and this were B. So we're going to do the same thing, but in a coordinate system. So we have our A, we have our B. The only thing remaining to do is now to join the origin to the head of B. Let me try to do that using a line, and there you have it. This is the final vector of A plus B. All right, now comes the interesting part. So we know our A vector looks something like this, but for clarity, let me draw perpendiculars from the head of A, and I do the same thing from the head of B. Let me do the same thing on the y-axis, and the same with the line B. All right, now our vector A, let me get rid of this is just for understanding. Our vector A, which is this blue line there, is actually ax I cap plus a sub y j cap. And that means that if I want to go to vector A's head from the tail, I must travel a distance of a sub x in the x direction, and I must travel a sub y in the y direction. So there you have it, that's vector A. Similarly, vector B would be sum b sub x I cap plus sum b sub y j cap. That means if I want to go from the tail to the head of B, that as in B vector, I must travel first in the x direction of a distance b sub x. So this here should be b sub x. And then in the y direction. So that means this length there must be b sub y. All right, so if you have A and B written as so, then what would be A plus B vector? So A plus B vector could therefore be written as A sub x I cap plus A sub y. So that's A sub y j cap. That's your A vector. We must now add that to B. So that's B sub x I cap and B sub y j cap right there. This would be our total resultant vector, something that we hope would be this, which it should be. Now look at the terms. You have I terms and then you have j terms. I terms are all the lengths in the x direction. So we can take this term here and this term here and combine them. And if I try to do that, I would get a sub x plus b sub x I cap. And I do the same thing with the j term. And by doing that, I get a sub y plus b sub y j cap. Now this is just simple mathematics. If you have terms like 2 times 3 and you want to add that to 4 times 3, what you do is you take 3 out as a common factor and then you add 2 plus 4. And this gives you 6 times 3, which is the same as if you would have evaluated these individual terms and written out the final answer, Or if you evaluate this, and that would also give you the final answer, which would be the same thing as before. So essentially what I'm doing here is I'm treating that I and j hat or j cap as the common factors of 3. And I'm taking them out as common, like here. So that's basic mathematics. And the reason I can do that is because I and j cap are vectors in the x direction, I in the x direction and j in the y direction. And this term here, or for that matter, this term there, or this one, are basically a magnitude, a number, multiplied by a direction vector. So that's a unit direction vector or a unit vector. So because it's a product, we can do the same thing. So this is valid. This is valid. This step here is valid by the rules of mathematics and nothing else. Now, if you look at this, this gives you a final vector whose length is ax plus bx in the x direction. So this is the if I have to call the resultant vector as r, so this length here would be vector r, then this term would be r sub x I cap. That means this is the movement, the length in the x direction for the vector r oriented in the space. And this term here is the movement in the y, so that would be r sub y j cap. So let's try to confirm whether this is the case. Looking back at our diagram, we have the resultant vector of a plus b drawn in this manner. Let me change the color. So this line here is the result. Okay, that's bad. This line here is the resultant vector, like so. And this is basically our vector. What we are saying is our r vector has some x component. Now the x component would be basically a perpendicular drawn from this head down to the base, which coincidentally matches with this perpendicular that I had drawn for the head of b vector. So that means this length here must be r sub x length, or the first term. And the length in the y direction, this length there, well, that must be r sub y. So let us see if r sub x and r sub y actually matches with these terms there. So r sub x must be equal to, from this equation, a sub x plus b sub y. Let's see if that is the case. We go back to the diagram and we notice that r sub x, which is this length here, is incidentally equal to a sub x plus b sub y, because if you add these two lengths in two parts, you get the total length, and that is the case for the first term. So that's this term right there. For the second one, for the y directions, we also have that, because if you look at the length here, this entire length from the origin line, from the x line to this line there, is the sum of b sub y and a sub y, which is the case here. So that is to say that our geometric method of adding vectors was correct. All we had to do was place them in this order such that the head of the previous vector now coincides with the tail of the second vector and add them in that manner. But this gives us another insight into adding vectors. Now, if you have two vectors, say a to be 2i cap plus 3j cap, and you have b vector as, say, 1i cap plus 7j cap, then in order to add the two vectors, all you need to do is add the individual components. So I would do that by considering the I components of the vectors. So that's 2 and 1. So the resultant would therefore be, for a plus b vector, would be 2 plus 1 I cap. And similarly, for the y components, which would be 3 and 7. So that would be 3 plus 7 j cap. If I add them together, that would be 3i cap plus 10j cap. That would be my resultant vector. Now, I really didn't have to do anything. I didn't have to, in terms of geometrically positioning and placing the vector and orienting them in certain directions, in order to know the resultant. With the help of I and j vectors, all I did was add the two components together, and that yielded the final answer. So that is the power of like resolving vectors in I and j directions, because that makes it so much more simpler. If you know a vector and you know the x components, which in this case is 2 and 1, and you know the y components, which is 3 and 7, if you want to find the resultant, well, that would just be the addition of all the components added in that order. So if you want to find the x component, that would be 2 plus 1, and y would be 3 plus 7, as I've done here. Now, not only that, we can also work out the difference of vectors. So if I take the same example again, 2i, 3j, and 1i and 7j, if I want to ask myself, wait, what is a minus b? Well, a minus b would be the same as a plus of minus b. And if I do that, that would be, let me write down a, that would be 2i cap plus 3j cap, right there, plus minus of, now let me write b, which would be 1i cap and 7j cap, right there. All I need to do now is to take the x and the y components together. So that would be 2 from the I here, and minus 1 from the j there, from the I here, sorry. And to do the same thing with the j components, that's 3 from there, and minus 7 from there. Now, 2 minus 1 is 1 I cap, and 3 minus 7 is minus 4 j cap. Therefore, my total vector, my subtraction vector of a minus b turns out to be 1i cap minus 4j cap. So as simple as that, I now have my vector subtraction and I also have my vector addition. So that is extremely simple. All I need to do is take the x and the y components and add them or subtract them in that order. Nothing more than that, nothing elaborate to this method. So the analytical method is therefore very helpful if you know the x and the y components of any vectors. You can do many operations on that. You can evaluate something like what's 2a vector added to 7b vector. If you want to do that, you need to multiply 2 with the components here, and you would want to multiply b with 7 and then add them up in that order. You would have gotten your resultant vector of 2a plus 7b. So that's another easy method, easy operation that you can perform. So all this really adds up in its simplicity, and that is why unit vectors in I and J are very, very helpful. So I hope this video made sense, and I hope it helped you understand the importance of analytical methods in vector analysis, and adding vectors in terms of adding them, subtracting them, and performing and carrying out many other operations that ultimately becomes really simple to perform. So hope it helps, and all the very best.